Okay, here's the difference. Listen. On the last problem, I was basically able to sketch what the area would look like roughly. Here I have a much harder time. And I don't want to use Plan B and go back and figure out all that I learned about quadratics. If you'd like to, you can. I just don't think most human beings, I don't know, I just don't like to do that. So instead, here's what I do. 99% of the time, if they're giving me an area on a calculator, non-calculator question, I can think of the region as simply being a curve and another curve. That's all I have to do. This isn't curved, it's actually straight, but who cares? Like, it doesn't affect how I solve the problem. All I have to think of is, I've got one curve, I have another curve. They intersect in some way to form a region. 99% of the time, they will intersect twice. Is there some remote possibility they'll intersect 3 times? Yes, but not likely. Question. So first task is to figure out the intersections. So I do that by finding where these two equations are equal to each other. Welcome to Algebra 2. I wrote 2 because I said Algebra 2. So before I do any calculus, I have to figure out where do the two curves intersect. Question. You now need a memorized flashcard. You need to look at this equation, remind yourself that you are looking at a quadratic. When solving a quadratic, you do not isolate the x. Instead, you group everything on one side of the equal sign and factor. But I don't like the x squared to be negative, so I'm going to move everything to the right. So this is going to equal 0. This will become positive x squared minus x. When you bring the 6 over it, it will become minus 2. That's how you solve a quadratic. Question. So keep track. We set the equations equal so we can figure out where the two regions intersect. Now we're solving the equation via factoring.
When solving this, could we just use our calculators and see when they intersect?
Yes, except that it's a non-calculator section of the test.
That's weird. Okay.
This is where all the students say lame. But,
so on this homework assignment?
On this homework assignment, you must do it this way. Otherwise, you are not preparing yourself for the AP test.
All right.
Now, as always in this class, you are on your honor to choose what is best.
I can't believe you would doubt me.
I don't doubt you at all. You just asked the question. I just answered it. Look out. I'm doing my best to be sarcastic, at which I'm not very good. The sarcastic answer is, there's no point picking up your calculator and doing it. Just look in the back and say the answer is A and move on, you know. So, right? Yeah, just, you know, I can't be sarcastic. Okay. Question. So factor. Reminder when you're factoring. I think pretty much everyone I've ever met gets confused when they try to think of the middle term, so don't. Just think of the last term. What multiplies to make 2 is 2 and 1. Now just multiply it out and see if it's going to work. So we get x squared. That would be 1x, 2x, and 2. I've got to somehow end up with this. So this has to be negative. This would also be negative. This would be positive. To make all three of these be the same thing, then, I need a negative, let's see. I need a positive here and a negative here. Hey, I promise, if you'll write all 3 lines and not do it in your head, you won't make a mistake. When you do it in your head, it's really common to make an error. So don't do it in your head. Just write it down. Make sure it works. So the solution is, one of these intersections is x equal positive 2, the other is x equal negative 1. Questions? So last thing I've got to figure out is is the curve on the top this equation, or is the curve on the top this equation? It's a really simple way to do it. If you can think of the way by yourself without me telling you, you'll remember much better. Just remember the key idea. When you're looking at this, you're not looking at a curve at all. You're looking at lots of points, lots of xy pairs. Same thing here. This one's pretty easy because every y value is just 4. So anybody have an idea of a really, really simple, easy, non-calculus test we can perform to figure out which curve is above the other? We've got the two curves. So really talk to each other, raise your hand and tell me, what's the really simple, non-calculus method for figuring out which curve is above the other? I've heard several people say it now, so. Show me your hands, you know. What's the easy test? What's the really easy test, Andy?
Just plugging in.
So what do you want to plug in?
Just the values in between -1 and 2.
Perfect. Stay with me. So I picked the easiest value I can find between x equal -1 and x equal 2. What value, Andrew, would you suggest is the easiest value to use? 0. This curve always has a y-coordinate equal to 4. This curve, at an x-coordinate of 0, I'm going to find the y-coordinate. I always use parentheses when replacing an x, or any variable. So I'm done. The top curve is this one. Okay. How many knew that before Andrew said it? Point to friend. Question? You would like me to talk through it again, talk through it differently. So the integral is simply, I'm going to integrate from x equal -1 to x equal 2. Curve on the top is right there. Curve on the bottom is 4. Question? So now I can erase all of that. You would just keep working down the page. I just ran out of room. So, to solve this problem, I would put those two together. I can use a rule. The antiderivative of -x squared is going to be -1 multiplied by x cubed over 3. This will become the antiderivative of x is x squared over 2. The antiderivative of 2 is 2x. You must have parentheses to indicate that the bar applies to all of it. Questions? Please.
Why don't you like to have parentheses around -x squared plus x plus 6? So
Oh, why do so? Are you asking Emma, why did we not need a parenthesis here and here?
yeah.
Doesn't hurt anything, but the leading set of terms don't ever need a parenthesis unless there's a negative here. This, like, the second set of terms would have to have a parenthesis if there's a negative here. So the blue are not required, they don't hurt anything. 2 points.
When do you notice change from like the intro to the Wilson?
Awesome. Right here. 2 points for Jane. I want somebody to raise your hand. I will pay you a full ticket if you will announce to the class what is the relationship between what I have circled in green as opposed to what I have circled in pink.
The green is before it's been, like, before you do the antiderivative, and pink is after you do the antiderivative, and, like, the same equation.
2 points. There's a better. You got the right idea. We need to say it differently.
Green is F prime and pink is F.
That's a good way. Watch. And it's what you meant. You have lots of these, so you're good.
Yeah,
Okay. What Matthew said is helpful. The green is F prime. Think of it that way. And the red is F. So it's right here. And that's how you know the switch occurred. When you've got the integral of F prime, once you find F, you don't need an integral anymore. You're going to do the bar instead. So this equation is what we're using to get from here to here. We're saying this equation right here with the integral and F prime is exactly the same thing as this with the bar and F. Question? Look here, please, everybody. In this version of the fundamental theorem, I use the symbols F prime and the symbol F. In this version, I use the symbols F and capital F. So I'll pay somebody else a full ticket to tell me how our, like Matthew already talked about how F prime is the derivative of F. Therefore, F is the antiderivative of F prime. This is the fundamental theorem as well. It's just using different symbols. You can use whatever symbols you want. What's the relationship between these two symbols? Okay, for an answer.
Are they just the same?
So how are they related?
It's like the antiderivative integral.
Better to say the antiderivative of F is what? 2 points. Somebody else help me.
Sorry.
Emma, how is, what I'm asking, hey, how is, in this equation, the integral of F prime is equal to F with the bar. F prime is the derivative of F. F is the antiderivative of F prime. This is the exact same equation with different symbols. So how is just the F related to the capital F? Emma?
F, just lowercase f is derivative of capital F.
Say it the other way around now.
Capital F is the antiderivative of lowercase f.
Okay. The whole point of all this is it doesn't matter what symbols you use when you write the fundamental theorem. What's important is to note when you're integrating the derivative of something, the fundamental theorem says that integral is equivalent to the antiderivative with the bar. Or you could say the displacement of the antiderivative. Or you could say the change in the antiderivative. That's the fundamental theorem. Did I answer your question, Jane?
Yeah.
Okay. Last thing to do here is just plug in stuff. So again, I always use parentheses when replacing a variable with a constant. Caution, everyone. strongly, strongly advise you to write out this step carefully like I'm writing it. On the written portion of the test, all you have to do is plug in the numbers with parentheses and you can quit. So if you carefully plug everything in, you will get the point. If you try to do stuff in your head, you'll likely make a mistake. This was Emma's question earlier. There's a minus here, and what's going to follow the minus are several terms. So you have to have a parenthesis. Over here, this minus only applied to the first term. It did not apply to the 3 terms, so there's no need for parentheses here. -1, -1 cubed, so in the FRQ section, you can quit right there, and you should quit. Continuing only risks losing a point. Multiple choice, you gotta go, yuck, I gotta find an answer, so keep grinding. So that's -8/3. That's 2. There's a 4. This would be -1/3, +1/3, back to -1/3. This would be +1/2, then -1/2. This would be -2, then +2. Question? All eyes up for a second. Look at me. Okay, here's a little hint you learned from experience. When you are working out an integral after you've plugged in the limits, you're just doing the arithmetic, the add, subtract, multiply, and divide. Remember, these 3 terms come from the exact same equation as these 3 terms. So I don't usually try to add all this stuff up first if there's fractions. Instead, I get it all written out, because usually there'll be a fraction over here that can be combined with a fraction over here, because they came from the same source. So that's where I noticed that these two will add to make -9/3. -9/3 is -3. That's 6, plus 2 is 8. Question? So then, since we don't have any room, so that's going to be 5 minus 1/2. That's 10/2, subtract 1/2, so 9/2. Is that the correct answer, please?
Yeah.
Question?
No, I'm just talking.
Not true.
No, I got the right answer, but it was like different and somewhere in the middle.
The arithmetic's a pain, in my opinion. It's not hard, it's just a pain.
So, could you rewrite that last step where it's like -1 x cubed over 3? Could you do like positive x cubed over 3 minus x squared over 2 minus 2x?
Say one more time.
Could you basically just like get rid of the negative in front of x cubed and turn it into like positive x cubed minus x squared minus 2x?
Oh, yeah.
No, because the negative doesn't apply to the x squared. It only applies to the x cubed.
This is what I'm saying. Like, it's like the idea that you have like
I really like that.
do that.
Yes, that's okay. Oh, no, not that. That's not the same thing.
Like, so you have to just do it.
Yeah, you can't do that. That's different.
You can't get rid of the negative 1.
This is the greatest picture of all
No.
time. Look at my face.
Anybody else here?